Hi students. So we've talked about endothermic reactions and we've talked about exothermic reactions, and now we're going to talk about a concept known as enthalpy. Enthalpy is the internal energy of a chemical under constant pressure conditions. So any given chemical has a certain amount of internal energy, and we refer to that quantity of internal energy as enthalpy. It's not possible to measure the enthalpy of a specific chemical in a reaction, but it is possible to measure the change in enthalpy as a reaction proceeds. So experimentally, if we carry out any reaction under constant pressure, we can measure the change in enthalpy, which is the change in internal energy as we move from reactants to products. And this symbol that we use for enthalpy is H. So here we've got this formula to calculate the change in enthalpy, and H stands for enthalpy in this reaction, and we have that the change in enthalpy, the triangle or Greek symbol delta is used to represent change. So the change in enthalpy for a reaction is equal to the enthalpy of the products minus the enthalpy of the reactants. And enthalpy is measured in kilojoules. And so it's a representation of the change in internal energy of the system. So when we're looking at a potential energy diagram, in the past we've looked at some exothermic and endothermic reactions. And so for example, I'm just going to plot an endothermic reaction here for a moment. Okay, so I've got my reactants going up to my products, and we can also plot an enthalpy diagram which looks just like a potential energy diagram. So we can either plot potential energy on the left here, or we can plot enthalpy in kilojoules. And we will use these somewhat simultaneously in Chemistry 11. So any energy diagram, potential energy diagram, can also be looked at like an enthalpy diagram here. So we have enthalpy on the y-axis, and again we're looking at the reaction proceeding as we go along. And so now when I plot my reactants, okay, my reactants have some amount of enthalpy, and I can also plot my products on here, and they have a specific amount of enthalpy, and it is the change in enthalpy that we are concerned with. So as we go, this is an endothermic reaction, so as we go from reactants up to the products, we are going to be able to experimentally measure our change in enthalpy. And so it is going to be equal to the difference between the products and the reactants. But it's important to remember the order in which we calculate it. And we are going to subtract the enthalpy of the reactants from the enthalpy of the products, so that here what we would see then is we're going up to a higher energy product or higher enthalpy product. And so our products have greater enthalpy, our reactants have less enthalpy, and so our delta H is indeed going to be a positive quantity here. Here are two enthalpy or potential energy diagrams side by side. So here on the left we have an endothermic reaction, which is similar to what we just plotted. And it's very easy to identify delta H just by looking at the energy diagram. Remember that in an endothermic reaction, energy is absorbed, and so our curve is going uphill, because our reactants are absorbing energy to make this higher enthalpy or higher energy product. So if we always start our arrow at the reactants, whenever you draw your diagram or you're looking at a diagram, if you start the bottom of your arrow from the reactants and you draw it towards the products, that will show you the direction of your delta H. So here, if I look at my endothermic reaction and I start from my reactants and we go up to our products, I can see that we are increasing in enthalpy here, increasing in energy, internal energy, and so my delta H for an endothermic reaction is going to be positive. It's going to be a positive value here. And that makes sense if you think about it for a moment. So if delta H is equal to the enthalpy of the products, so final minus initial, products minus reactants, okay, here I don't have values to work with, but we can just think about it for a moment. Here we had a bigger number. Okay, so we are going up in energy, so we've got a large quantity for our products, and we're subtracting a smaller number. Right? Products are higher than reactants on our enthalpy or potential energy diagram. So it's going to be a positive value here. Okay, depending on how big this hill is, it might be a very small positive value, but nonetheless, it's going to be positive. It's not going to be negative because we are going up in enthalpy. It's an uphill process. In an exothermic reaction, the opposite is true. In an exothermic reaction, heat is exiting, or energy is exiting the system into the surroundings. So as we move from reactants to products, we are actually seeing a loss in internal energy of the system. The enthalpy of the products is much lower than the enthalpy of the reactants. And again, if we follow the same process, if you take your if you draw an arrow on your diagram, always starting with the reactants and moving in the direction of products. So if I started with reactants here and I move down to my products, you could also draw your arrow over here if it's just easier for you. Okay, starting with reactants, moving down to your products, I see that I'm going downhill or down in enthalpy. And so my delta H is going to be negative here. Okay, the energy of the system is decreasing because I'm losing energy to the surroundings. And again, this makes sense if we think about how we calculate delta H, or I should say the formula that we use for delta H. So delta H, change in enthalpy, is equal to the enthalpy of the products minus the reactants. And so here, this time, as we move down towards a lower enthalpy product, we have a smaller number and we are subtracting a big number. Okay, and so the change in enthalpy here is going to be a negative value. Again, how the magnitude of that negative value will depend on how big this hill is, okay, or how much energy was lost to the surroundings, but it's definitely going to be negative because our reactants, what we started with, we had more enthalpy, and we moved to products that have lower enthalpy, and so when we're subtracting a bigger number from a small number, we're always going to get a negative value here. So this is a summary of enthalpy, changes in enthalpy for endothermic and exothermic reactions. Putting these into practice is a little bit more complicated because you need to find for yourself a process or a system that makes sense to you. So when you approach a question, for example, like this, and the question is, what is delta H? There's a couple of different ways that you can think about this. And the question could also be, is this endo or exo, which we've dealt with before. Okay, or the question might even ask you to plot an enthalpy diagram. And so the process that is going to, there will be a process that clicks for you and makes sense to you, but I will go through a couple of them that usually make sense to students. And often, many students find that for any type of question that involves changes in enthalpy, just sketching a really quick enthalpy diagram is enough to help them figure it out. Other students rely on this equation right here. Delta H is equal to products minus reactants, and that's enough to help them. So it really just depends on, something's going to make sense to you, and that's what you should use. But let's work through a couple problems together and come up with some solutions. So here's an example. We've got a reaction equation. Carbon plus oxygen gas gives us carbon dioxide plus 3,903 3,935 kilojoules. So let's answer all the questions for this. First of all, is it endo or exo? Okay, we can go back to our earlier lessons and remember that where we have heat on the product side, that means that heat is exiting the system. Therefore, this is an exothermic reaction. So there's step one. What is the delta H for this? Well, I know that for this reaction, the value is going to be 3,935 kilojoules, but is it a positive or a negative value? Okay, they've used this example has used a comma. I'm not sure if the comma is actually supposed to be a decimal, but for now, let's just treat it like a comma. Okay, so there's the magnitude of the change, but we need to decide whether it's a negative or a positive value. So you might just sketch yourself a little diagram. You know this is an exothermic reaction, so if you were to draw yourself a super quick diagram, think about what an exothermic curve looks like. We always start with our reactants having higher energy, and they're going to move down to the products. Okay, so if from reactants to products we are going down in enthalpy, which means that delta H is going to be negative. So that's one way that we might be able to determine that this is going to have a negative value for delta H, from the fact that we know it's an exothermic reaction and we can draw ourselves a curve for an exothermic reaction. Another way to think about this could be knowing that it's exothermic again, to recognize that if energy has been given off, our reactants must have had higher energy. So the enthalpy of our reactants must be a larger number compared to our products. So when we subtract the reactants from the products, we're going to get a negative value. Anytime we subtract a bigger number from a smaller number, we're going to have a negative value as an answer. So that's another way we might just think about it theoretically. Another possible question that we could be asked here is which of the chemicals, the reactants or the products, have had the greater enthalpy. And again, it would come down to thinking about looking at this reaction. You could either decide that it's exothermic, which means that reactants had more enthalpy to begin with and we moved to lower enthalpy products. That's one way to think of it. Or we could see that because the heat term is on the right hand side and we know that energy must be conserved here, that over here we must have had the greater amount of enthalpy in our reactants, and our products have lower enthalpy as a result. Let's do another example of this here. I'm going to make this into a decimal point for clarity. And here I've got a reaction. Again, it's asking me, is it endothermic or exothermic, and what is the value of delta H? So I see that the heat term is on the left-hand side this time. It's on our reactant side. And when it's on the reactant side, that means that energy was put into the system, heat entered the system, and therefore this reaction is an endothermic reaction. Now for an endothermic reaction, you could just memorize that delta H, if we look back here for a moment, we could say, okay, delta H is negative for exothermic and positive for endothermic. I don't find that's very useful. For you, it might help you, but if you mix it up, then you're going to get a lot of wrong answers. It's better to think about it in terms of what's happening in the reaction if it's endothermic. So again, just drawing yourself that quick little diagram is a great way to do it. An endothermic reaction, we're putting energy into the system. So as we move from reactants to products, we're going uphill because energy is being absorbed. And so here's our reactants on the bottom, here's our products on the top. And if we draw that little arrow from the reactants to the products, it's going up in a positive direction. So our delta H is positive. It's going to be a positive value because energy is being absorbed by the system. So our delta H for this reaction is going to be positive, and the value would be given here, okay, because the heat is in the already shown in the reaction. So 169, we'll say 0.4 kilojoules, and it is a positive value. Here's a reaction where we're given the delta H. Okay, and so we need to know, is this an endothermic or an exothermic reaction? And again, sometimes you can memorize it, but just thinking about how we calculate delta H here is a great way to solve this. So remembering that we always subtract the reactants from the products. So if this value is a negative value, think about what that means for a minute. In order to get a negative value, when we're the quantity that we're subtracting, this must be the bigger number in order to have a negative value. So that means that our reactants have higher enthalpy than our products, and we could quickly sketch ourselves a little curve of that. If your reactants have higher enthalpy, that means they're up here compared to your products down here, and this is an exothermic reaction. Another way that we might approach this, okay, if we were to not use this equation whatsoever, is to just think about what our energy diagram would look like with a negative value. So again, draw our diagram, and we say to ourselves, well, if it's a negative value, if I always draw my arrow from my reactants to my products, in this case, my arrow would be going down. If delta H is negative, the internal energy in my system, or my enthalpy, is going down. So then it's just a matter of filling in the rest of the curve. So if I already have, I can quantify my change on my diagram, and now I can just simply fill the rest in. So this is clearly an exothermic reaction because I'm starting at a higher amount and I'm coming down to my products. So there's my reactants and there's my products, and so this is an exothermic reaction. There's more than one way that you can approach questions like this. You might get questions thrown at you in all different forms. You might be given delta H, you might be given a reaction equation, you might be given a potential energy diagram, you might be given a word problem. And just making sure that you understand the connection between changes in enthalpy, changes in energy, and what's going on in the reaction is the key critical part. You can approach these questions in any way that makes sense to you, but a really helpful way is to sketch yourself a little potential energy diagram, or just think about how we calculate enthalpy. It's always products subtract reactants. I hope this is helpful, and I really encourage you to try some of the questions, and by all means check your answers in the back of the books to make sure that you're doing them correctly. Best of luck.